First of all, thank you for joining us today. So in this presentation, I will introduce some improvements of logical application over the past few years. Okay, first, I would like to introduce myself. I'm Hayato Kuroda, and 29 years old, living in Japan. I have been working at Fujitsu, not that this is gold sponsor, and since 2018. Over these years, I have been submitting and reviewing patches related to logical application. My colleague, Hou-san, also applied to this talk, but unfortunately, he could not be here today. Okay, here is the agenda for this talk. First, I will introduce the basic architecture of logical coding and application. Next, I will describe how large transactions are decoded on publisher and how such transactions are subsequently applied on subscriber. Following this, I will discuss the next enhancement called parallel apply. Okay, let's start the introduction. I will talk about two concepts, logical decoding and logical application. Logical decoding is an infrastructure that transforms all persistent changes into another format. The specifics of format are determined by output plugin, so user can change based on their motivation. And basically, this output can be interpreted without needing the detailed knowledge of the internal database internal state. So typically, this feature can be used to migrating databases from Postgres to MySQL or Oracle or something. Logical decoding is implemented based on the write-ahead word. The consumer process reads word and by decoding them, extracts data in plugin-specific formats. Output plugin modules provides rich callback functions to allow user customization based on their requirements. Users can refer to example plugin test decoding or the built-in default plugin PG output. Or another plugin can be found when you check the Postgres wiki. Okay, then let's take a look at the workflow of logical decoding. Okay, when words are generated by backends, the consumer process reads and decodes these word records. The decoded results are then stored in the consumer's memory. These stored data can be consumed either by calling SQL functions or by using the streaming replication protocol. The bottom box, this one, shows the example. We can see that insert statement is extracted like the following highlighted line, where the PG logical slot get changes function. Okay, if the decoded results are consumed by the streaming replication protocol, they are sent to downstream and cleaned up when the transaction is committed. This mechanism is deeply used by the logical replication. So let's move on to the next topic. Okay, logical replication is a method of replicating data objects and their changes based upon the replication identity. It uses a publish and subscribe model. The upstream node is called as publisher, and downstream is subscriber. Compared to the physical application, the logical application allows fine-grained control over both the data replication and security. So user can choose which operation is transferred or not, or something. The Postgres documentation records some typical use cases for logical application. such as sending incremental changes, replicating between different measure versions of a platform, and so on. Okay. To use the logical application, first, the publication must be defined on the publisher node. The publication has a responsibility to control which tables and operations are transferred. The users can create publication via create publication command, and information will be added to the PG publication system catalog. The above box showed example, and it seems all of operations insert, update, delete, and truncate will be replicated to downstream side. And then, to receive changes, the downstream must subscribe the publication. The relationship can be created via create subscription command, and information will be added to the PG subscription system catalog, like bottom box. Okay, this sequence diagram represents the workflow of logical replication. The left side illustrates the publisher, and the right side is subscriber. Logical replication is built with an architecture like physical streaming replication, and it is implemented by two processes. One is word sender, and another one is apply worker. The word sender process reads and decodes words by using the logical decoding infrastructure. So when backend generates word, the word sender checks the generated words and decodes. When the transaction is committed on publisher side, the decoded result called replication messages are transferred to the apply worker by using the streaming replication protocol. And then the apply worker applied the received all messages in the correct transactional order. Okay, the progress of logical replication can be monitored through the system views. On the publisher side, users can check the PG start replication view. As you might know, it contains one row per word sender. So both at physical and logical word senders may be listed here. You can distinguish word senders by using the application name attribute. In the normal case, application name is the same as subscription name. The above box shows the example, and the application name is set to sub. The name of maybe it is the same as subscription. Similarly to physical application, users can check the current position of sent or applied words like sent LSN and reply LSN, and time lag between them. Replay lag. Okay, regarding the subscriber side, users can check the PG start subscription view. It contains one row per apply worker, and we can distinguish them by the sub-name attribute, like highlighted line. Apart from publisher side, this view provides information about when the worker received messages and last received word location, like these attributes. Okay? Alright, we have covered the basic concepts of logical decoding and replication. Now, moving on the core of this presentation, I will discuss how large transactions were handled in logical replication in earlier versions. Okay, first, let's check the workflow of logical decoding and replication in version 12. As denoted by the left square, this one. Compared to normal case, there is an extra step involved when dealing with large transactions. To avoid excessive memory usage caused by large transactions, each top-level transaction can store only 4096 changes, fixed value. If number of changes exceeds the limit, the decoded results are spilled to file, temporary file. When the transaction is committed and the commit record is decoded, the word center must first restore the decoding result from the temporary file and then send all of the decoding results to the subscriber side. Okay, this sequence diagram provides an overview of the workflow. As written in the left square, the publisher side, the word center writes a decoded result to temporary file and read it before sending to subscriber. So here is a question. Is there anything that could be improved? Let's dive into how the community enhanced this processing in version 13. Okay, as previously discussed, Postgres 12 cannot precisely control memory usage by word center. It means that controlling memory usage is a challenge, and if the publisher node has a large amount of memory, it seems to be inefficient because there are a lot of free memory, but word center can use only fixed value. Yeah, to address this issue, the Postgres community has introduced a new configuration parameter called logical decoding workname in version 13. This parameter sets the maximum amount of memory usage that can be used by logical decoding. The default value is 64 megabyte and the minimum is 64 kilobyte. Okay. Here is a modified workflow of word center in PG13. As highlighted the left square, the same position. And the condition for writing to disk has been changed. In PG13, the decoding size of all transactions is monitored. Yeah, when the decoding size exceeds the specified limitation, the largest transaction will be chosen and word center will write it to temporary file. This operation will be continued until the memory usage becomes lower than the limit. Overall, this improvement is aimed at the logical decoding phase. So here is the question. Is it sufficient? Is there anything that could be improved? Let's take a look at how the community improved this processing in version 14. Okay, as I said before, transactions are only sent to subscriber after they have been committed. Consequently, large transactions may trigger network congestion, so it may apply lag. That's right, maybe one. Okay. To address this issue, the community introduced a new subscription parameter called streaming in PG14. This subscription parameter specifies whether in-progress transactions can be streamed for this subscription. By default, the parameter is set to false, so all transactions are fully decoded on the publisher and sent to the subscriber, same as previous versions. The below box shows an example with the parameter streaming with true. Okay. Here is a modified workflow of word sender in PG14. As highlighted the left square, red one. And when the decoded result exceeds the memory limit, the word sender can stream a chunk of transaction and clean it up. The transmission of chunk begins with a new application message, stream start, and conclude with stream stop. This cycle exceeds the limitation and sending a chunk. This cycle repeats until the transaction is finished on the publisher side. At the end of the transaction, the world sender sends one of three new replication message: stream, commit, abort, or prepare. It depends on the final state of the transaction. If the publisher node the transaction was aborted on the publisher side, the world sender must send stream abort. Okay, I will provide the revised sequence in PG14. As I discussed earlier, the world sender sends stream chunks whenever the decoded result exceeds the limitation. The backend generates word and world sender decoded, and when it exceeds the limitation, it's streamed. It streamed all messages. Okay. Upon receiving these chunks, the apply worker stores them in the temporary file. In PG13, changes are spilled to disk on the publisher side, but in this version, it is done on subscriber. Once the apply worker receives stream, commit, or prepare, it loads all replication messages from the temporary file here, and then start to apply large transactions. Okay. Additionally, since PG14, the system view for monitoring has been added. It contains data with one row per logical replication slot, so it is meaningful on publisher side. This view stores statistics related to logical decoding, especially how many chunks are spilled to file or streamed to subscriber. The above box showed example with streaming is disabled, and we can see that spilled count and bytes and number of transactions are incremented. It seems that approximately 90% of transactions has been spilled. So in this case, DBA should change either of streaming parameter or the buffer size, GUC. The below example shows this case streaming enabled. And we can see that streamed count, transactions, and bytes are incremented. DBA can monitor the view and adjust the parameters accordingly. Now, in PG14, the world sender can start streaming earlier, and more convenient way to tune parameters is provided. So here is the same question. Is it sufficient? Is there anything that could be improved? How do you think? The answer is not enough. The performance of replicating large transactions still has room for improvement. For example, as I just mentioned, disk read and write operation may be required on either the subscriber or publisher. Even if the streaming is true, the received changes are spilled to disk on subscriber. And the subscriber will start to apply large transactions after the transaction has been committed on publisher side. So how community improves them? From here, I will talk about the next enhancement developed in PG16 called parallel apply. Okay, parallel apply is an alternative approach for handling large transactions. This feature was committed in January and could be available in the upcoming release, PG16. It allows the subscriber to be set to the parallel mode. And when parallel mode is enabled, the subscriber applies stream in progress transactions immediately without waiting for commit message from publisher side. Furthermore, the subscriber can process these transactions in parallel. Okay? The advantage of this feature is quite simple. It enables faster and more efficient handling of large transactions. Unlike in previous versions, the subscriber does not wait for the commit message, resulting in reduced total elapsed time. Moreover, while operating in parallel mode, the subscriber does not have to serialize any replication messages to a disk, which means that resource usage can be decreased. This feature can be widely used when if users allow streaming or intermediate transactions, and particularly, it can transport the batch operation on the publisher node. This slide describes the usage of this feature. To enable parallel apply, users must set the subscription parameter streaming to parallel. The above box, you can see that, demonstrates an example of creating subscription with streaming is parallel. The status of whether the parallel mode is enabled or not can be checked by using the substream attribute. And if it is enabled, the value will be P, like highlighted one. The parallelism of this feature can be controlled by new GUC parameter called max parallel apply workers per subscription. Okay. This sequence diagram provides an overview of the internal architecture. The workflow on the publisher node left side is not changed. When the chunk transaction reaches the subscriber side, the apply worker starts a new background worker called parallel apply worker and pass the received messages to it. When the parallel worker receives the messages, it applies all of them as soon as possible without waiting commit. Okay? Once the transaction is committed to the publisher side, this information is passed to the same parallel worker again, and then data becomes visible on the subscriber. In this talk, I will dive deeper into the parallel apply worker and its workflow. Okay, a parallel worker starts when in-progress transactions are streamed from the publisher side. The normal apply worker is responsible for controlling parallel workers. So in this talk, this process is sometimes referred to as the leader apply worker. Okay. Multiple parallel workers can run per subscription, and the parallelism can be controlled by the new GUC, as I said before. In the left diagram, the value is set to 3 because there are 3 parallel apply workers. Each parallel worker is assigned up to 1 transaction, and this assignment will never be changed during the apply handling. The leader apply worker communicates with parallel workers through the dynamic shared memory and shared message queues. There are 2 queues per apply worker, and 1 queue is used for passing replication messages to parallel worker, while another queue is used for receiving messages from parallel worker. Okay, next, I will explain the workflow detailing how processes handle in-progress transactions. The left side represents the leader, and the right side is parallel apply worker. When the leader worker receives the initial chunk of an in-progress transaction, it launches a new parallel worker, it assigns it to the given transaction. Then the leader sends a message to the parallel apply worker. The received parallel worker then applies these messages immediately without waiting anything. If streaming stops, the assigned worker waits until it receives the next chunk of messages. When the reader receives the next chunk from publisher side, it resumes passing to the same worker again, and it begins applying messages once more. Okay? When the reader worker receives the prepare or commit message, it sends the received messages through the assigned parallel worker and waits for it to finish the applying transaction. The parallel worker performs the actual prepare or commit operation and marks the transaction status as finished. Subsequently, the reader worker removes the relationship between streaming transaction and parallel worker. If there is enough space in the worker pool, the parallel worker can be reused for other in-progress transactions. Note that the commit prepared operation is handled by the reader apply worker. Okay? The presence of parallel workers can be checked by reading the PG stat activity and PG stat subscription views. Regarding the PG stat activity, the status is set to active when the parallel apply worker handling the large transactions. The above box shows the case, but the status is idle. So now, at that time, the parallel worker does nothing. Yeah. In the PG stat subscription view, the tuple corresponding to the parallel worker has a valid reader PID. However, some attributes related to received time and LSN are null because the parallel worker does not directly receive the messages. The below box shows the example, and maybe the first tuple is corresponding to the parallel worker. Okay. Next, in this section, I will discuss failure handling. Okay. Like the normal apply worker, the parallel worker exits if it meets an error. But before exiting, it puts the error message in the shared message queue and sends a signal to the reader apply worker. When the reader becomes aware of the issue, it pops the message from the queue, reports it to the server log, and exits by itself. After this, processes follow the same procedure at non-parallel mode. The launcher restarts a parallel worker and requests the apply worker requests the streaming data starting from the last received LSN. Yeah, then the world sender starts sending data from the requested point. Yeah, additionally, if users want to skip the transaction, they can check the final LSN of the remote transaction from the server log, and it can execute alter subscription skip command. Okay, but one big difference from the non-parallel mode is sometimes the final LSN of the remote transaction cannot be recorded on the server log. This occurs because the streamed in progress transaction initially lacks the final LSN, which is assigned at the end of the transaction. As I mentioned earlier, the parallel apply worker begins applying changes before the commit operation. So there is a possibility the failure may occur before the transaction has a final LSN. In this situation, users must disable parallel mode once and trigger the same conflict again. The normal worker will start applying transactions after the commit on publisher side, so definitively the final LSN will be appeared in the server log. Okay, next, in this section, I will discuss some challenges of implementing parallel apply particularly avoiding deadlocks. This feature introduces concurrency to logical application, which brings along additional risks of deadlocks. The deadlock might happen if tables that independent on publisher becomes dependent on subscriber. We encountered 3 considerations while development, but yeah, due to time constraint and some complexity, I will introduce only one of these cases, the simplest one. Yeah, let's assume a scenario: 2 transactions being executed on the subscriber side. So one transaction is handled by the parallel worker PA, and another one is done by the reader apply worker LA. Okay, for example, there is a table that stores the name and population of Japanese prefectures. On the publisher node, there are no constraints on the table, but on the subscriber, there is a primary key. The ID is added. Now, LA is waiting for PA due to the primary key constraint, while PA is waiting for LA to send the next stream of changes of transaction. In this example, Kanagawa tuple is first modified by PA, but LA tried to modify the same tuple. At this point, LA cannot receive messages because it freezes. It cannot move forward. It cannot do anything while waiting. So LA also cannot move forward because it cannot receive other next chunk from LA. Okay, this situation results in a deadlock. The Postgres lock manager cannot detect the deadlock because parallel worker does not wait any locks. It just waits a message. Okay. To address this issue, we introduce a new session level lock called stream lock. This lock is acquired by using the subscription ID and related transaction ID. The LA acquires lock before sending stream stop and release it before after sending stream start or transaction final message about prepare commit. As for the PA, it acquires the same lock after processing the stream stop message and release it immediately. In the example provided earlier, the LA has acquired the stream lock at this time, and PA tried to acquire it as well. So now we can see that the wait for lock becomes cyclic. The LA has acquired the stream and tried to tuple, and PA has acquired the tuple and tried to stream. Okay? It becomes cyclic. Therefore, the Postgres deadlock manager can detect the deadlock and abort either of the transaction. Okay. Next, in this section, I will present a result of performance testing, focusing on the latency of a bulk insert workload. To begin, a synchronous logical application system was built, and some tuples were inserted on the publisher node. The elapsed time from insert to commit was measured and compared. The number of inserted tuples were depending on the test. And for this test, both the publisher and the subscriber are located on the same server. Okay? Parameters and executed SQLs are listed in the below box, so you can check now. Okay? Here next is the result. This plot result. Okay? This plot compares the elapsed time between parallel and non-parallel modes. The horizontal axis, x-axis, represents the number of inserted tuples, while the vertical axis represents the elapsed time from insert to commit. So lower is better, okay? While testing, the logical decoding work memory is set to 30 megabytes. Yeah, although it may be quite trivial, but the number of inserted tuples significantly impact in all cases. And the round plot, blue one, represents the non-parallel mode, and triangle plot, red one, represents the parallel mode. As evident from this graph, the elapsed time is improved in all cases, with around 40% improvement for this workload. Okay, next. In this plot, the logical decoding work memory is varied, and the horizontal axis represents that. The number of inserted tuple is fixed at 5 million. Unlike the previous plot, the parameter does not impact the elapsed time. Perhaps because the stream transaction is much larger than the decoding buffer. And the improvement of elapsed time is also similar at around 40%. Okay, finally, I will discuss the future of this feature. Our team aims to extend parallel apply to normal, non-streaming cases. The basic idea is largely the same: to launch parallel apply workers whenever the subscriber side receives a new transaction. So receive, launch, receive, launch. Okay? Some mechanisms, a basic workflow, and some efforts for detecting deadlock can be reused. We have not designed yet, but theoretically, if the size of the stream transaction is becomes smaller and smaller, the overhead might not be negligible. Yeah, and latency improvement not be as significant as the current case. Furthermore, deadlocks could be more likely to occur. Yeah, anyway, please don't miss the next approach to enhance the feature. Yeah, final summary, this final slide. Logical application is a powerful feature that continues to evolve. However, one significant issue with logical application has been handling large transactions. Initially, the publisher node occupied considerable memory, but since PG13, this has become controllable. From PG14, the publisher could stream in-progress transactions to the subscriber side. With PG16, such transactions can be applied more quickly by using the parallel apply feature. Our next goal is to extend this feature to normal case, further enhancing the logical application. If you have any questions or suggestions, please contact me, kuroda.hayato@fujitsu.com. Okay, that's it. Thank you for listening.